going to be what? V1 what? Plus J plus K. And let's say we wanted vector W. And I don't want to call it W1, but what's vector W going to be? W1I plus J plus W3K. So do you agree that that could be any two vectors right there? Are you okay so far? Okay. W is going to be these bars. He hasn't told me what those are yet, but it's going to be I, J, and K across the top. And then what do I write next? V1, V2, and V3. And then what? W1, W2, and W3. Okay, so at least I have some sort of notation. Now, is that something I could do anytime I have two vectors? Absolutely. I, J, and K are going to stay the same. I, J, and K are going to stay the same. But what's going to be different? V1, V2, V3, W1, W2, W3. You okay so far? Now you're just going to do the same thing 3 times. It's really simple. You are going to circle I, and you're going to cross out the row and the row and the column that it's in. And what does that leave you with? How many of these? 4 of them, right? Then you're going to do the same thing 3 times, and this is the first iteration of it. You are going to write V2 W3 minus V3 W2. How did I get that product right there? It's an X. You multiply those two, and then you subtract the product of those two. Are you okay so far? And then what do you think you put next to that? I. Because which one did you cross out? I. So what do you think you're going to do next? Circle J. Do the same thing. You crossed out the row and the column. And then I'm going to write this underneath. Okay, I'm going to write this underneath just so I can show you everything. V1 W3 minus V3 W1. And what's that? J. So then what do? Circle the what? You do this, and then you have V1 W2 right there. And then what? And do you see how I kept them in kind of a T, U, V, W, kept them in alphabetical order? W1, and what's that? K. What have I not written? I've left something out. What have I not written in there? That's a vector, right? Are they all going to be pluses?
Isn't it minus?
Yeah, and this is the only tricky thing, is that it goes plus, minus, plus. It goes plus, minus this one, and plus that one. That is the only tricky. See that minus sign right there? Tons of things get missed, and this is why it gets missed. I'm going to show you where the book is really annoying in its definition. So do you see this right here? Everybody take a look at that. What do you notice about the blue box right here? What do you notice about the blue box? There's something in that line.
Oh, they switched.
What did they do?
Oh, that's
Do you see this? It's a plus right there. And why is that stupid? What did they do? What they write and what we wrote is the same thing. What did they do?
They just switched.
They took these two. You see that right there? And they switched the order to change the sign. Bad. Bad book. Bad. Bad. Don't do that. Because what's easier to memorize? This system or this, just flat out? The system is much easier. The system is much easier. What you have actually found right there is you have been finding discriminants over and over again. Determinants over and over again. Determinants is something you're going to find in vector land over and over again. So just to see if you can guess at this, how many 2x2 determinants did we calculate? We used 3 2x2 determinants to calculate 1 3x3 determinant. Where are the 2x2 determinants? Here's one of them. Here's one of them, and here's one of them. We used 3 2x2 determinants to find 1 3x3 determinant, and we use that in the cross product. What's really cool about this is this is a vector. Do you agree? This is a vector? Yeah. So theoretically, could I give you 2 vectors, and could you use this formula right here? Sure. Let's say V was equal to, I don't know, what do you want V equal to? How about 1, 4, 2? And let's say W is equal to 2, -1, 5. Those are 2 vectors in 3 space, right? So they're sitting there in 3 space. 2 vectors form a plane. Find me the cross product of those two vectors using that formula. Go. Do that right now by yourself. So what do you end up with for a coefficient with 22? 22i? Then what? Minus j? Is it minus j? Right? Is it minus 9k? Something like this? So that right there represents what? What does that represent? The cross product. So that vector right there is perpendicular to v and w, and its magnitude is equal to the parallelogram formed by v and w. That's pretty cool. If I gave you that question, I said, like, find the area of the parallelogram formed by two vectors in 3 space, you know how much work that is? If you didn't have this formula? Think about it, everybody. If I just had 2 vectors in space, you'd have to, like, draw it out, calculate angles, and, like, it's not trivial. It's not trivial. How comfortable you are doing the math, not understanding where it comes from, but doing the math I just showed you. How comfortable are you? What do you think? Doing okay-ish? Okay-ish? So we just started at 3 dimensions, which is usually where we go to. Let's go back to 2 dimensions for a second, because I could ask you a question like this. Let's say the vector, I don't know, I don't want to use j. Let's say the vector v was actually the vector 3, 4, and the vector w was, I don't know, 2, 6. So those are 2 vectors, right? What can you form with 2 vectors in 2-dimensional space? You can find you can form a what? Form a parallelogram, right? So you could have, again, these are not to scale. You could have vector v and vector w. And what could I ask you? The parallelogram, right? I could ask you the area of the parallelogram. So, like, what is the area of this parallelogram? Well, do you have a formula for that? I gave you that right at the beginning. Do you remember what it was? What's the area of that parallelogram going to be? V times the magnitude of times what? Sine theta. So are 2 of those things pretty easy to find? Yeah, so what do you get here? So you know the area is going to be equal to, what's the magnitude of V? It's going to be the square, 5. Hey, 5, that's nice. Times what? Square root of 40 times what? Sine theta. So do you have a way of finding theta? Yes. How do you find theta? The dot product, right? What does the dot product tell you? How do you use the dot product to find? Well, what's the dot product? You know that v dot w is what? Magnitude that times what? Cosine theta. But what's the algebraic definition? v1w1 plus v2w2, right? So what is the algebraic dot product? 6 plus what? 6 plus 24 is going to equal what? 5 times the square root of what? 40 times cosine theta. So you know that theta is going to be cosine inverse of what? 30 over what? 5 square root of 40. So theoretically, we now take this right here, and where do we plug that in? Into there. So theoretically, do we have enough ammo to find the area of a parallelogram in 2 space? We do? We do. We absolutely do. Do you want a quicker way? Yeah. Would you like a quicker way? Yeah. You want a really fun way? Yeah. You already know it. So what did we use? We used this system right here. There's a highlighted piece there that actually summarizes what we need to do. What little tiny piece do you think correlates to finding the area of a parallelogram? Which little tiny piece of all the work up there? Close. What's next to those? What's highlighted in yellow? A lot of the same thing over and over again. So guess what you can use a 2x2 determinant to find? Oh, it's super cool. Check this out, everybody. Up here, I skipped over this. Wanted to come back to it. The area of a parallelogram is v1w2 minus v2w1. So what does that say? Well, look at this. Have you already done 3 of these, or 6 of them, so to speak? It's v1 times w2 minus v2 times w1. So what were those 2 vectors we came up with down here? What were they? They were those 2, right? So if you want to do v cross w, what is it again? 3, 4, 2, 6, right? So what's that going to be? 3 times 6 minus 4 times 2 is going to be? Is what? All done. Pretty cool, huh? So when we did it out over here, theoretically, when we do this out, I'm a little wary because that's a lot of complicated radicals and stuff. And what should that come out to? Ready? 5 times the square root of 40 times sine of what? Cosine inverse of 30 over 5 root 4. Can you do that on your calculator just to see if we're remotely right? I'm curious. I went out on a... So now we have a really quick way of finding the area of triangles too, because what do you get when you cut a parallelogram in half? What do you get when you cut it in half? A triangle. Look up here, everybody. Up here. What's half of a parallelogram? A triangle. So do you have a quick way of finding the area of any triangle given the vector definition of two sides? Absolutely. What's the one thing we haven't done? I've just given you some really cool formulas. What have we not done? Correct. I want to show you the picture for how you derived the two-dimensional version of this. You will need to understand it, and I want you to understand it not as you're going to be asked on the AP test, because this material is not on the AP test, and I'm not asking it as a bonus, but no, I'm not going to give you this flat out as like an entire quiz.
It's not going to be a quiz.
This is way harder than what a quiz would be. My point is this, the reason I'm showing you this is if this is the work you need to do the two-dimensional one, I really don't want to have to do the three-dimensional one in too much depth. I want you to understand how it works, less the specific minutia. So what do you have here? You have two vectors. Well, what's going on? Let those two vectors be two non-parallel vectors in two space, because what happens if you have parallel vectors? Can you create a parallelogram? No, you can't create a parallelogram with parallel vectors.